Okay, we've been talking about thermodynamics here. So we got into chapter 16 and talked about some thermodynamics. Remember, the idea of sort of thermodynamics is one of the main sort of questions a lot of times that we look at is whether or not a reaction, again, is spontaneous. And as we talked about last time, when we were talking about something being spontaneous, again, sort of in this sort of thermodynamics realm, we are looking at whether or not, again, the reaction will take place under those particular conditions. Again, it really doesn't have too much to do with how fast or slow the reaction will take place. If it does, again, that's more kinetics. But here, just, will this reaction occur if you give it enough time? Will it actually occur under those conditions? Again, as we talked about, you can have some reactions that are spontaneous that are really fast, and you can have some reactions that are spontaneous that are really slow as well. So again, that's sort of the idea of spontaneity, is that the reaction will take place. A couple of things that we talked about in terms of ways to maybe determine whether or not a reaction will be spontaneous or not. We revisited our delta H, which is our change in enthalpy. And again, a reminder, if it is negative, that is an exothermic process. And if it is positive, it is an endothermic process. And we introduced the idea of entropy, which is S, or delta S, we sometimes look at it. And when we look at delta S, that has to do with the amount of disorder there is in the universe, or whatever you're looking at. So delta S does increase, actually, or become more positive when we have more disorder. So when there's a lot more disorder, we end up getting a sort of positive value for delta S. Vice versa, if we sort of decrease the disorder or increase the order, however you want to look at that, we will see the delta S sort of go down and become more negative as the disorder decreases, which again would imply that the order increases. One of the ways we could look at sort of entropy and help us determine whether or not a reaction will be spontaneous is we could calculate the delta S of the universe. And delta S of the universe is equal to delta S of the system, or your reaction, plus the delta S of the surroundings. So pretty much the way that we calculate the delta S of our system here is basically you take all the delta S's of your products, which is your final state, minus all the delta S's of your reactants, which is your initial state. Remember that entropy is a state function, which basically means it doesn't really matter how you get there. The two important spots, again, are where you start and where you end. So kind of your final and initial state. And again, in a chemical reaction, obviously our final state is our products, our initial state are our reactants. That goes with our delta S of the surroundings, and that is equal to minus delta H of the reaction divided by the temperature in Kelvin here. And again, that negative is in the formula here for surroundings because, as we talked about, there's sort of an opposite relationship in terms of what happens with the surroundings and the entropy based on the delta H of the reaction. So if a reaction is exothermic, it's going to release all that heat and energy to the surroundings. Surroundings will pick up all that heat and energy and cause a lot more disorder as they have a lot more energy, everybody flying around sort of in the surroundings. And we will see an increase in the entropy of the surroundings. And again, that's because if it was exothermic, my delta H value would be negative. Negative and negative would turn my delta S into a positive value, which would imply increase in the amount of disorder of the surroundings. Vice versa, if the reaction is endothermic, it will be sucking out basically the energy from the surroundings, and that will allow everybody in the surroundings really to kind of slow down, if you want to think about it that way. They're not going to be flying around as fast. They're going to kind of slow down, and that's going to create a lot more order, a lot less disorder that's going to happen. And when we look at this equation, again, our reaction is endothermic, our delta H would be positive. Along with that negative would then turn our delta S for the surroundings into a negative number, which again would imply that overall we're seeing a decrease in the amount of disorder. Now, We could also make a fairly good prediction when we look at the delta S of the system. And remember that if we make more gas molecules than we started with, we would predict that the delta S there would be positive, and vice versa. If we actually consume more gas molecules than we make, we're creating a lot more order. Also, when we go from different phases, that is definitely where we see some change in entropy. Solid, which is a pretty ordered sort of stage, will have a much lower entropy than something like gas molecules, which are flying around going crazy, and they would have a much higher entropy value and more sort of positive value. Now, remember that if we do calculate delta S of the universe and it is basically a positive number, then that reaction will be spontaneous. And obviously vice versa there. If it's a negative number, it will not. If it equals 0, as we talked about, it would be a equilibrium type of condition. We then got into the idea of Gibbs free energy. And Gibbs free energy is basically the energy available to do some type of work. And that's delta G is typically what we have. And with Gibbs free energy, as we will see, there's multiple sort of formulas that you could use. One that you could use is just the basic delta G, kind of like all other thermodynamics sort of calculations. You could take the delta G of your products and minus the delta G of your reactants. And there's also one that does relate all the other sort of thermodynamic sort of values together. Delta G equals delta G equals delta H minus T delta S. And when you use this equation, again, unit-wise, you do have to be careful of these two. Again, delta H is typically kilojoules, and delta S there is typically joules. So you want to make sure that you're not off by that factor of 1,000. When you use those together, usually will involve some type of conversion. And with that being said, delta G is usually also given in kilojoules in most cases. So we can actually use delta G to help us determine if the reaction is going to be spontaneous. And typically, if you have a negative delta G, the reaction will be spontaneous. And if you got a positive delta G, the reaction typically will be non-spontaneous. Any questions on any of that stuff there that we talked about here last time? All right, then let us pick up. I think last time we finished up looking at actually this equation. And remember that based on conditions, you can make a pretty good prediction as to perhaps if the reaction is going to be spontaneous or not. If you know sort of the delta S value, not really value, but if you know the sign of delta S, or you know the sign of delta H, and you know sort of what temperature, you can make some predictions on it. And again, you will come across a lot of questions sort of based on that by just making predictions without actual numbers. So let's take a look at temperature and sort of its effect on spontaneity. So here we have this reaction of calcium carbonate breaking down into calcium oxide and a little carbon dioxide. Here at 25 degrees, the delta H value here is 177.8 kilojoules, and the delta S is 160.5. So why don't you calculate the delta G for this reaction? And is the reaction spontaneous at 25 degrees Celsius? So take a moment there and see what you come up with. Okay, so let's take a look. So obviously here, like I said before, there are a few different equations or sort of formulas that involve delta G. And as I mentioned last time, probably the best piece of advice is just to use the formula that sort of goes with the information you have available to you. So obviously in this case, we do have a delta H given to us, and we do have a delta S given to us. So it clearly would make sense to use the formula that has both of those guys in there. So we'll use our delta G is equal to our delta H minus T delta S. So putting in our numbers here, delta G will equal our H, which is 177.8 I am again going to multiply by 1,000, and that's going to convert that into joules, so I don't have any issues with the units on both of these guys. Again, you do need to do a conversion on one versus the other. It doesn't really matter which one you do, but that's the way I'm going to do it. We're going to go minus our temperature, which does need to be in Kelvin, so 273. It's going to give us our 298, I believe. And here we have 160.5 joules, right, per Kelvin per mole. All right, so if we do all that good stuff there, we got 177.8 times 1,000 minus 298 times 160.5. Gonna get us 1,29971 joules, or roughly about 130 kilojoules in this case. Again, if you divide it by 1,000 there at the end, we'll get you 130. First off, any question on the calculation at this point? We ended up with a delta G that is positive. That means at 25 degrees, this reaction is non-spontaneous or not spontaneous, right? And by the way, we could sort of predict that based on what we talked about before. Again, when we look at this equation that we used, we ended up here with a positive value of H, and we also had a positive value of S. Remember, again, because this guy's in kilojoules, this guy's in joules, that would require, in order for this reaction to be spontaneous, a pretty high temperature for that to occur. And that would be the only way that this back part, the negative part, would outtake the front part that's positive. And obviously at 25 degrees Celsius, that's not a high enough temperature for this reaction to be spontaneous. Any questions on that? Now, could we actually, if we wanted to, determine at what temperature this reaction could become spontaneous? And the answer is we actually can use this equation in a situation like this if we were curious to know at what temperature this reaction would turn spontaneous. So we know definitely that when this reaction would be spontaneous, our delta G would be negative, which means if we set our equation delta G equal to 0 and go delta H minus T delta S, and if we basically solve for temperature, which I'll go right here, I think. We'll move that temperature to the other side there, equals our delta H, dividing this to the other side. Gives us our temperature would equal our delta H divided by our delta S in this case. And if we put that in there, we'll temperature would equal, again, here we have differences in units, so we need to get them to the same unit. So on the delta H, I once again am going to multiply by 1,000 to get it to joules, so that it will cancel out correctly with the joules we got going on basically on the bottom there as well. So if I do that, we will end up with 177.8 divided by, or times 1,000, then divided by 160.5. That's going to give us about 1,108 Kelvin, which if I subtract 273 from to convert it into Celsius, that would tell me that approximately the temperature I would need, the minimum temperature that I would need for this reaction to become spontaneous, is a whopping 835 degrees Celsius. I would say that qualifies as a high temperature that would be necessary in this particular case. Now we know, just looking at the graph here that they have on here, that that is actually the case, because when we look at the graph, this is temperature versus pressure of the CO2. And since CO2 is the only gas in this case, the only way we could have pressure is if we produced, right, CO2. And that would require this reaction to basically take place. And we can see on the graph here that really it doesn't really happen until our number right there of 835 degrees Celsius is basically when that occurs. Now, if you look at the graph, you will see that it actually does start to increase before that. And what we're talking about here is we actually don't hit 1 atmosphere standard pressure until about 835 degree or 835 Kelvin, which again would be that minimum temperature for this reaction to be spontaneous. So this equation, as you can see here, can be used to determine, for example, if a reaction would be spontaneous. And if it's not spontaneous, you could actually use the same equation to figure out at what temperature it would become spontaneous. Any questions on that there? All right, so why don't you give us a go, see what happens here. For this reaction, delta H is minus 1204 kilojoules. Delta S is minus 216. At 25 degrees, are the reactants or products favored at equilibrium under standard conditions? So see what you come up with here. Okay, so once again, let's take a look here. We got our delta H, we got our delta S, so we should roll with our equation again that has both of those guys in it. Here we are at 25 degrees, so that's going to turn into 298 Kelvin. And we'll put in here, so we'll go with our delta H. Again, I'm going to multiply by 1,000 to get that guy into joules. And we'll go minus our temperature there, and our delta S we could leave there, negative 216.4, it looks like. So we will end up with negative 1204 times 1,000 minus 298 times negative 216.4. Looks like perhaps negative 1139513 joules are roughly there, I think. Negative 1140 kilojoules, give or take. Yeah. Question on like calculation. Again, obviously, like I said before, if you wanted to, you could convert the S into kilojoules and it should come out the same. Now, at this point, we do have a negative delta G. That should mean that this reaction is spontaneous and should mean that really it should head in this direction, which means products here should be favored in this case, right? Any questions on that? Again, as we talked about as well, just based on the signs of each of those things, we had a negative delta H. We also had a negative delta S, which turned this into a positive, basically. And that means at low temperatures, this side should be much bigger, and it gave us a negative value for delta G, and that's what we see here. So at low temperatures or regular temperatures of 25 degrees, that's enough for this reaction, obviously, to be spontaneous. You would need a relatively high temperature to make this reaction non-spontaneous to occur. Any questions on that there? All right, so we talked a little bit about phase changes earlier on, but when we talk about phase changes and sort of Gibbs free energy, we know that a phase change happens at the same temperature. So when we look at this here, this liquid to gas, or even the gas to liquid, if this was, say, water, like in this example, this would occur at 100 degrees Celsius. And at 100 degrees Celsius, as we talked about, there's a certain amount of heat required to do that. That is the delta H of vaporization, or the heat of vaporization. And for water, that is pretty much that number you see down there, 40 point, we'll call it 79 kilojoules per mole. And that is, again, specific for water. And when we would do this, we could actually figure out the entropy of vaporization, which is sometimes referred to. So basically the entropy change as we go and change the states. So when we do this, our delta G would equal 0 because this is an equilibrium process. And if we rearrange this equation and move our temperature delta S to the other side like we did a second ago, But actually, in this case, we're going to divide our temperature to the other side. We get our entropy of vaporization is our delta H divided by our temperature. Temperature here, like normal, does need to be in Kelvin. This is the equation I was talking about earlier. If you rearrange this equation and solve for something like the delta S of vaporization, you get this equation here, delta H over T. Should not be confused with the one that we saw earlier, which is for the surroundings, has a minus delta H over T. Yeah. So surroundings will have the negative if you're going to solve for something like a phase change, the delta S of vaporization. You could also do it for fusion as well, the solid to liquid conversion. If you're going to solve for that, which is based off the delta G equation, there is no negative sign in there. So again, that is sometimes very much confused by people. They either put the negative where it shouldn't be, or they forget the negative where it should be, and that type of stuff. So don't get that confused. Again, here, this is for our surroundings, and it should have a negative as we use our delta G equation and rearrange for something like our phase change here and our delta S of our phase change. It does not have the negative. So if we do this calculation, this is our delta H of vaporization for our water. That is 100 degrees Celsius converted to Kelvin, which is how we get to our 373, which is, again, the normal boiling point. And if we do this and put these numbers in, we get a delta S of, again, sometimes referred to as vaporization, of 109 joules per Kelvin. Now, this makes sense because we're basically doing this transition as we go from liquid to gas. And that basically means that we're going from a more ordered state to a more disordered state when we get into gas. And again, we would expect a delta S here to be a positive number. Now, let's say we're doing perhaps the opposite, which is condensation, right? So we start with water in the steam, basically, or gas state, and we take it to water in the liquid state. This is basically condensation, right? And let's say we wanted to calculate our delta S, and we could call it condensation. Why not? Condensation is our delta H over T in this case. Again, it would still be the same number, and it would still be basically the same temperature because it occurs at 100 degrees Celsius. The difference is here, as we go from gas back to liquid, it is a exothermic process, right? Which means really our delta H of vaporization should actually be a negative number. And that would then get us a negative 109 joules per Kelvin. And that would also make sense based on the way that we're going, as we're going from, again here, gas back to liquid. So a more disordered state to a more ordered state. And that should result in a delta S that's actually negative. So you can use this in either direction. Really, the only thing that will change is the sign on the heat of vaporization, depending on which way you're actually going. Like I said before, you could also do a similar calculation for our solid to liquid conversion or backwards. Remember, that occurs, for example, for water at 0 degrees Celsius. And for water, the delta H of fusion is approximately 6.02 kilojoules per mole. Again, it would be a positive 6.02 kilojoules per mole if we were doing basically melting ice, basically. And it would be a negative 6.02 kilojoules per mole if we were freezing the ice, as it would be exothermic. Now, it's also important to remember that if you're going to do this calculation for any substance that is not water, you will have probably different heats of vaporization, heats of fusion. They will be different numbers. And also the boiling point and freezing point or melting point of those things will also be different temperatures if they're not water. So obviously these numbers here are specifically for water, but if you're using some other substance, you would have to find the corresponding correct delta H of vaporization and fusion, and also the corresponding temperatures at which those things would change the phases. Any questions on that there? All right, so why don't you try that one here? The enthalpy of vaporization for mercury is 58.5 kilojoules per mole. The normal boiling point here for mercury is 630 Kelvin. What is the entropy of vaporization? Okay, so let's take a look. So again, obviously enthalpy of vaporization, so that's the delta H of vaporization here. And as you can see, again, it's a different number than it is for water, as we're dealing with mercury in this case, rather than water. Also, our normal boiling point here, temperature, is different than it is for water. So, and it's actually already in Kelvin, which is really good. So we can use our delta G is equal to our delta H minus T delta S here. Again, since we're at a phase change, that's going to equal 0, which allows us again to sort of rearrange this equation. And here we are going to solve for our delta S here, which will be our delta S of vaporization. And that would be our delta H divided by our temperature. It's already in Kelvin, so that's good. So we'll go with 58.5 kilojoules over our 630 here. And that will get us something like 58.5 divided by 630. Get us something like 0.0929 kilojoules here. We could times it by 1,000 since delta S is typically given in kilojoules, or joules, to gives us 92.9 joules. Again, here we're assuming that we are going from liquid to gas in this case. And that again makes sense as we end up with a positive number, as we should be increasing the disorder. Clearly, if we were doing something like condensation, really the only difference here, that would then become a negative, and basically that would then become a negative, and so that one, I guess, as well. So if we were doing condensation, really that would be the only way there. You would know you're doing condensation because it would probably mention something like you're kind of doing condensation, or you're going from, obviously the gas back to liquid. So it mentions stuff like that. Otherwise, obviously, you could roll with the idea that it's going from liquid to solid, which again would give us obviously positive numbers here like we had originally. Any questions on that there?